All right, so in this lesson, we're going to look specifically at trig functions. Believe it or not, I've tried to record this about 3 times, ditched it every time, and I think this is the 6th set of PowerPoints. I've been working on them every night until 1 or 2 a.m. and then scrap them the next day and start over. So hopefully this one's going to stick. I'm not doing it anymore. So hopefully it makes sense to you. And if you have any questions, please let me know. So we're going to look at trig functions in the Cartesian plane. So we're going to be looking at an XY plane. We're going to briefly touch just a refresh of how graphing is written, like just how you write your X's and Y's and where they go in a plot. And then we'll kind of look at, well, what happens when we have a circle in the plot and how that impacts some of our numbers and how that impacts our angles. So hopefully it'll be relatively clear for you. I find this section a little more challenging, primarily because it's a bit of an abstract concept, especially when you get thinking about the different phases and waves, but it's actually really useful for you to at least have thought about it enough that when you hear some of those terms come up, if you're going to industry conferences or reading industry papers, that you'll be aware of what the terms are, at least from a math perspective. I'm certainly not an expert myself, but I will give you, at the very end, when I'm going to give you your trade example, I'll give you a little bit of background as to where I've used some of this and how looking at periodic cycles or waves can be really helpful tools for analyzing things. So the very first thing I want to look at is I want to look at the coordinate system. So as most of you, I'm sure, are aware, we typically, there's several coordinate systems we can use in math. There's a polar coordinate system, and that kind of touches on a little of what we'll do today. But what we're really going to look at is the XY Cartesian plane. So it's just a 2-dimensional plane. We're not going to deal with 3 dimensions. And Y is always going to be our vertical axis, always, never changes. And X is our horizontal axis. Now, if we were thinking in terms of specifically analyzing things in math, along our x-axis, X is the variable that changes what Y is going to be. So we'll find in physics when we get there that time is always on our x-axis in equations because we can't control time. It's independent of our control, but we can control the outcome at that particular time, which would be our y-axis, or might be the distance you've gone. You can control your speed, so you can control your distance, but you can't control the lapse of time, that kind of scenario. So that's just a convention you'll have, is there'll be certain things you'll notice always end up on the x-axis. So x-axis is horizontal. If you're like me and you tend to flip things around, especially if there's 2 of something, I flip them around. The, T-H-E, I often will spell it T-E-H. I have my computer set to autocorrect. I have issues flipping letters. If you're a number flipper, I get it. So for me, what I do, I think X, it took me a long time to remember these. You start graphing in junior high, probably grade 7. You might have even touched it in grade 6. And it wasn't until grade 11 or 12, I guess it would have been grade 11, it was when I was doing physics, that it really stuck for me which axis is which. So I was a slow learner. The x-axis is always your horizontal axis. Now, because I flip things around, what I always think is across is horizontal. So X is the horizontal one and Y is the vertical. One of my students last year told me his teacher must have been similar to me, maybe had a hard time remembering. It always said Y to the sky, just because they remember to remind you that the Y was the vertical component. So just a couple of really easy little tips to remember: X-axis and Y-axis. Now those 2 axes are simply number lines. The numbers aren't written on these ones because I want to put some values in. Where the 2 of them cross, we call the origin. At the origin, the value is 0. I'm not sure why this does this sometimes. The value is 0. So it's 0x and 0y. That is our 0 point. From that point, we define all other points. So along the x-axis, now in this particular grid, each square is worth 1. We can tell that because of what we see up here. So as we move towards the right, we have positive x values. That means as we go to the left of the origin, we're going to have negative x values. If we go vertical, if we go up, that's our positive values, and down is our negative values. Now that's good to keep in mind because when we get to our physics, we're going to find we use the same conventions. When we think about directions and we want to figure out, well, how do I describe a direction? In order to describe a direction, what we'll do is we'll say, well, it is a positive direction or a negative direction, depending on whether it's moving left or right, or east, northeast, south, and west. So we'll give you some of those conventions. So knowing how these line up is really helpful. Now, let's look at a couple other things that are labeled here. There are 4 quadrants. Quadrant, and I don't know why they're numbered in this order. I don't have a good reason for you. There's a couple things in this section I really don't have a good reason for. They seem counterintuitive. Quadrant 1 is the one that gets used most often. So this is quadrant 1 in here. I'll switch to my pointer. It might make it a little easier to see. So here we have quadrant 1, this section. We typically work in positive values simply because a lot of times we're recording something against time, and so far we can't get negative time. So this is our quadrant 1. Then quadrant 2 is counterclockwise to that. Okay, so quadrant 2 is over here. Now in quadrant 1, you'll see any number, any point on this side will have positive x because it's to the right of the origin, and a positive y because it's above the origin. When we're over in quadrant 2, we're to the left of the origin, so it's going to always have negative x's, but it will always have a positive y. So we might just take a minute and actually write those down just to help us remember, because this is going to be really useful for us. So whenever you write coordinates, it's always x and then comma y. That's how we write them. So if we're in quadrant 1, we have a positive x and a positive y. If we're in quadrant 2, we're going to have a negative x and a positive y. Now when we get down to quadrant 3, you can see any point in here, let's say we use this point, any point in here has a negative y because it's down. It's to the left, so it also has a negative x. So quadrant 3 is going to be the negative quadrant. Everything is negative in there. And then in quadrant 4, we find, well, we're below the x-axis. So any point in here is below the x-axis, so it's on the negative y side, but it's to the right of the origin. Lefts and rights, I get mixed up. It's to the right of the origin, so it's going to have a positive x. So it's always going to have the pattern plus minus. So those are just, if you're trying to figure out where numbers go or what values should be, knowing which sections are positive, negative, or positive, negative are really useful. And we can do that just by looking at a simple number line. Here we have the point 2, 3 labeled on the graph. First, and I've got that noted here, but I know people will flip it around. The first point is always going to be your x, and the second one is y. The way I remember that is it's in alphabetical order, x, y, z. All right. So that's just a quick refresh of how we would read a graph. Now let's take 2 seconds, and why don't we label the points that I've popped in here? So I've labeled a couple points. Let's call this point A, and we'll call this one B. So what are the coordinates for A and B? So we know they're going to have the form x, comma, y. So now what we want to do is let's for A, let's figure out, well, what is the x value? So if we were trying to figure out what the x value is, we're going to go over 1, 2, 3, 4. Each of our squares is worth 1. So we've gone 4 to the left, which means we have a -4. And then we're going down 2, which means we have a -2 for y. So that would be -2, -4. If we go over to this corner here and we look at point B, we are going, let's do the X first. So we're going 1, 2, 3, 4, puts us on at the line where B is. So we're 4 positive, and then we're going down 1, 2, 3, 4. So over 4, and then down 4 is going to be -4. So that's just as simple as it is to write coordinates. You'll be expected to be able to write coordinates for a couple points on a graph. All right, so why do we say this relates to trig? Well, you're going to have to give me a second, go through another, maybe the next slide it might click in where it relates to trig. So we're going to be looking at functions that are the result of periods and phases. And these two sections that we're coming into, I broke them into 2 chapters, and this is kind of the end of the trig chapter. And then we're going to take trig and we're going to apply it in vectors. I don't know if breaking it was a wise move or not. It's just broken in name. You would have the PowerPoints in the same order. So it's all the same at the end. So on this particular circle, I would like to know for this point, this red point, what are the X, Y values for that point? Now, it actually could be quite easy for us to figure out. So we'll look at how we would solve that. We want to know what are the X and Y values for it. So we're in a section where we're often going to see a circle, which a circle, well, we can tell, we know what the radius of this circle is because it's 3 blocks high. So this length must be 3. That happens to be our hypotenuse, because the radius is the same all the way around. And then we have a radius of 3 over here as well. But more specifically, I'm not going to go all the way across. We're going to erase a little bit down here. We can use a triangle. We can use a triangle with an X and Y value to tell us what is the X and what is the Y coordinate of that particular point, if we know how many degrees of a turn we've made in that circle. So that's where a lot of our questions are going to come from. So that's what we'll be looking at, is at different points on a circle, can we identify the height difference? We'll think of it as height because we can think of it as turbine blades. If those blades were turning, as those blades turn, the tips get higher and higher and higher. You get to a maximum point and then they start to drop. They're going to go that distance below the hub and then back up to, if we call horizontal, or 0 point, and they'll keep, and that height pattern is going to keep going, and we're going to get the same pattern repeat itself over and over. So this is where it's going to relate to trig, as we're going to see some of this triangle come in. A triangle's been written really, really nicely here. Now, if you've done some calculus, you would have talked about unit circles. And what a unit circle says is that as these points, as we go around the circle, a point on this side will have the same coordinates as a point over here if the triangle has the same dimensions. The only difference is on this side, their X's and Y's will be the same, but this one's going to have a negative X value instead of a positive X value because if this angle matches this angle, they are the same triangle. We're going to use that information a little bit. You'll see the information that we're using that in the next lesson. We'll see a little bit more of it today, but not a huge amount. Now we could draw another triangle that also has the same points. And we could draw it down here. We could draw a triangle with the same height. Well, I didn't draw very nicely. Sorry, things aren't lining up very well. We could draw a similar triangle down the bottom. Get this lovely bow tie shape. And I actually have a slide that shows all of that for us. So if the angles are the same, this triangle will have the same sides as this triangle. So that means I'm going to call this, we'll call it again XY. Over here, this one's going to have the points negative X, comma, Y. Down here, we're going to be, remember the negative, negative, we're in quadrant 3. So negative x, negative y. And then in quadrant 4, in this quadrant, we're going to have a positive x and a negative y. But they will be exactly the same x's and y numbers. Now, why is that important to us? That's important to us because it's going to help us solve some vector challenges that we have. But it's also important because it means that these graphs are going to share the same numbers in numerous places, which I think, if I remember what I put on the next, yeah, I did. If I remember what I have next, I have this lovely graphic. So, and this has, oops, I guess I can't pause it when I'm in presentation mode. So if you want, I can upload the slide that has this exact graphic, but you'll see this point rotates around the graph, okay? And as it rotates around the graph, it creates a wave function or a wave pattern if we plot the sine of the function and the cosine of the function. Now you'll see here, see how sine is a horizontal dotted line? That's because the sine of the function is going to be related to the angle of the turn that we've made and the hypotenuse. That's what gives us that horizontal piece, the x component, we call it, of the triangle, versus the vertical one. The vertical one comes from the cosine function. So we'll see those values change. There's a slight difference over when they peak and when they hit their lows. This would be our center point. You'll see, I wish I could pause this, because the center point here, where we would say cosine is 0, you see x has its maximum at that point. We'll look at that in a couple graphs that aren't moving all the time, make it a little easier for us. So that's what I have here, is I've stopped the motion and I've put extra labels in. And I said, okay, what do we get? What do we get for shapes? What do these functions look like? So the two functions here, we've got a function. A function just means an equation. Function is kind of just a little bit of a geek word. It doesn't mean anything really special, other than with a function, you put something into it and it calculates something and gives you something out. So we say this is the sine function. We put an angle into the sine function and it puts out whatever the y value happens to be. So that's all that a function is. So for this particular one, we have our sine function up above here. And if we put the angle 0 in, so if I was to draw a circle, and I guess I didn't label the angles on the circle, 0 degrees is always going to be where the origin is. 90 degrees is straight up. Horizontally, we get, oops, I almost went 270. We get 180. And then if we go straight down, I'm going to erase that and write that a little better. We get 270, okay? So those are our degrees that we happen to have in the circle. And we'll kind of look at what values match up with those particular pieces. Now, give me just a sec here. Looks like I got a purelator order and the dogs have gone crazy. Sorry about that. I have a dog that goes absolutely insane for the mailman or the purelator truck, and I'm not sure exactly why. Just goes absolutely ballistic for it. All right, so let's see if I can remember where I was. So you're looking at the circle and we said, okay, let's treat our circle. It's kind of treating it like a clock, and we'll put the degrees of a circle in. So circle is 360 degrees. So we start out, where did my pen go here? There we are. We get, okay. So 0 degrees is along the x-axis. 90 degrees is our positive y. Negative x, this is just our negative x. That's our 180, and then 270 happens to be our negative y. So that gives us, and it's always labeled counterclockwise, exactly the same as labeling quadrants, okay? So what this function says, it says, okay, if you're at 0 degrees, the triangle at 0 degrees, well, there's no triangle there. We'll sketch our little triangle this way so we can kind of visualize what's happening. So we know what the angle is. That's our x value, and we want to know, well, what's the height of this? Now, these graphs, the height of the graph, the amplitude is really the radius of our circle. So that means our hypotenuses are 1. Okay, so this comes from a unit circle. We don't have to worry too much about that right now. But if we look here, this is our angle here. If I want to find the opposite side of the angle, I'll have to calculate that using sine. If I want to find the adjacent side, I'm going to find that using cosine. Make sense? So if I take a value, and maybe x and y might not have been the best things to use here, but if I have this particular triangle and I want to know what's the height when the angle is 0, well, when the angle is 0, there's no height, which means the sine must be equal to 0. And if we look here, that's exactly what we get when we have no height. The sine of the function, so that's our vertical component, is 0. The cosine value of 1 is 1 because the triangle only has a length. It doesn't have a height, so basically it's a straight line. Now let's say we're at 45 degrees, so we'll go here somewhere in the middle. And we have the same radius. If we draw our triangle, now we have a height and we're going to have a length. Well, what are those heights and lengths going to be? Well, the height matches up with sine if we look at trig. So if we find 45 degrees, there we are. This is going to be our height, and 45 here, the values happen to be the same. And it's hard to guess exactly what they are. You can plug them into your calculator to find out exactly what it happens to be. 7071. I had that on the tip of my tongue, and every once in a while I second guess it. So this point right here, if I was to put, right where I drew my red dot, if I was to label that as x's and y's, because I'm assuming this is put on an xy graph, it would have a height of 0.7071 and a length of 0.7071. So both of them are the same. I kind of should have said them in the backwards order, but they're both exactly the same. And we can find that for any point on our graph. We could draw a point over here, and let's say I've drawn a point right here. And I want to know, well, what's the value? What's the x and y at that particular spot? Well, let's say that this is 15 degrees. Okay, so what's the x and y for that at 15 degrees from horizontal? Well, the first thing we're going to have to do is, that's not 15 degrees from 0. So we'd figure, well, from 0, how many is it? Well, this is actually all the way 180, and then you go a little bit more. So this is actually 195 degrees. So if we go and we look at our graph, well, 180 is here, 195, somewhere is right about here. There's one of our values. And if we go across, it's going to be somewhere maybe 0.9, something like that. And then for our sine value, we're kind of in the same area. There we are. These graphs are shifted slightly. There's my 180 and 180. So we're somewhere right around here. Negative 25, roughly negative 0.25 for our sine. So it doesn't have very much height. And then our cosine makes up our x, and it's going to be maybe negative 0.9. You'll notice both of the values are negative, but that's because that point in the circle, when you are around 195 degrees, you're in the quadrant where everything comes out negative. Okay? And I find that really kind of abstract to explain. And I don't necessarily know what the best way to explain it is, but hopefully that kind of gives you an idea of how we can use those two to connect the trig with those circly things and the graph that we had. Now, there are a few keywords that you need to know. And I probably should have done the keywords first here, but it didn't really matter which order. So the keywords that we need to know that you'll find is every one of these graphs has a period. Now, these circle ones have a period of 360 degrees because the values keep changing. And then I get around to 0 and I can still keep going. So you'll notice we go 0 to 180. We're back at a 0 again. We hit the next 0 point and then the pattern continues. So the period for this particular function, for the sine curve, a period is 360 degrees. Okay. Now let's say you had a burr on one side, on two spots on your wheel. And this was a wheel that's turning. You might have a slightly different period. Okay, so you can get some variations by having symmetry in circles. But for circles, we're typically looking at a period of 360 degrees because it's 360 degrees for a full rotation. Amplitude is just the height. So amplitude is just the height of the peaks. Now, in a good sinusoidal function, the amplitude will stay the same. So the amplitude is the height from 0, and here we have the same amplitude. This is amplitude as well. It should stay symmetrical. If it's not symmetrical, well, then something's happening, something's going on. And then a phase shift is just when a graph has been shifted over, forwards or backwards. So you'll notice the cosine graph and the sine graph look pretty much the same, except, see this high point here on the cosine graph? The high point on the sine graph is ahead 90 degrees. So we could say, well, cosine is just shifted back 90 degrees. So that's what we call a phase shift. It's when you take a graph and you shift it ahead slightly or you shift it back slightly. And there's things that can cause phase shifts. Now in electricity, there are phases because electricity follows these sinusoidal functions. And I know that's kind of weird concept because you can't see electricity. And for years, scientists were even really messed up with it as to is electricity, is it a wave, is it a particle? Where does that kind of stuff fit in? What is electricity? Because it falls kind of under the light spectrum. And there's still lots of kind of weird science about it. How do electrons work, which is electricity. And Heisenberg's particle in a box theory is not one I ever want to teach to you guys. I had to go through that a couple times in university. I haven't looked at it since, thank goodness. I do have my old books if you really, really want to look. But that's where you're going to use these is in electricity. So in electricity, we'll have 3-phase electrical circuits. You're going to deal with those with Andy. We use those a lot in industrial electrical. So whenever you put a motor, it causes a phase to lag, holds it back. If you put an inductor in, and an inductor is full of extra charged energy, and it causes a lead. So you have these lagging, because we've got motors, but we've also got inductors, or we've also got capacitors that are causing inductance. We've got leading and lagging currents, and they cause phase shifts. So they cause these currents to shift, and when they shift, when we put them all together, it changes the amplitude. So we're going to look at that for just a second. So here I have 2 curves. I've got the sine curve, and I've got it in blue. It's the blue dashed line in the bottom one. And what I've done is I've said, well, let's take this sine curve and we're going to shift it by 90 degrees. So I'm giving it a 90-degree phase shift. And that's what's happened here. You see the peak was 90 here, and now the peak is at 180. So we've shifted the phase 90 degrees. What happens if those 2 waves combine to make a new one? Because that's what happens with electricity. Your phases come together. And what happens? Well, here you can see the amplitude is the same when we adjusted the phase. The amplitude, the height stayed the same. The period stayed the same. It's still going from 0 to 360 here, 90 to 450. That's still 360 degrees. What happens? Well, if we look here, I've got 3 graphs now. What I've done is we've got our blue line, which is our sine curve. We've got our green line, which is our shifted sine curve. And then what I did was I took this 2, and in Desmos is a really cool graphing calculator app. I'll put a link up for you if you want to play with what these curves look like. I took the 2 and I added them together. So, well, what would it look like if I added those 2 curves together? And we get this purple one. Now, what's happened? See, the purple curve has a larger amplitude. And that's because at this point, right here, you get the 2 values of these 2 curves, the values. So you get 0.75 and 0.75 roughly. I know I'm approximating. They add together to give us almost 1.25. So we've added it together and it's making our graph even higher in spots. But here we find it's making it even lower. And there's actually some really cool stuff you can do is if you change the phase, change the period so that it doesn't follow exactly 360 degrees. That might be like having a couple of teeth broken on a gear, or having something that wobbles symmetrically. So it happens twice every turn. That would create a different period. And you get these kind of weird curves and they add together. You get super high peaks, and then you might get some that are extra low or smaller peaks in the middle. So you'll see we kind of get a graph that goes halfway in the middle. You'll see here, balances out, everything shifts a little bit. We get a whole new curve that happens. And that's kind of what we're going to be doing when we add vectors together. We're not going to do it with a graph, this section. There's really no calculations you really need to do for it. It's very much just, this is what it looks like. This is how it could be used. And very lastly, where would you use this in your trade? Now, you're never going to sit there and calculate a whole lot of that sine and cosine stuff. I shouldn't say you won't calculate it. You won't analyze graphs of it a huge amount. You're going to calculate vector addition because you need to figure out how has electricity shifted when we've added a capacitor, or if we've added a motor to a particular circuit. How does that change the circuit? That matters to us because we don't want to have something overloaded. We don't want to cause something to blow. We don't want to be drawing too much current, those kinds of things. You're going to deal with that with Andy. But there is another spot where you actually do use these curves that have periods. Now, if you look here, see where it says vibrations, and you see this picture here. This is a sine curve. I say sine curve, we often call periodic functions. We use sine curves in order to show them because that's what gives us that constant curve. And well, how would that relate to a turbine? Well, here we have a large peak and then it goes down. Then we get another large peak and it goes down, another large peak and then it goes down. And this looks at, it's great for turbines because as turbines turn their circle, they have a period. Every turn, 360 degrees. And if you keep track of those turns and the vibrations that occur during those turns, if a vibration changes, that means something inside the turbine has changed, which means perhaps there's maintenance that needs to have happened. Now, the advantage to using sine curves and analyzing them, and it's way more complicated curves than the one I gave you, but there's usually programs for subtracting things out and adding things in, and you're looking for usually changes in the function shape. So you kind of get, okay, this is what it usually looks like, and oh, there's a change, there's a new peak showing up, something like that. So they can use that to predict what's happening. The advantage to that is you can have a sensor plugged in on a component in a turbine. Like in a gearbox, gear's a great spot for listening to vibrations. There's tons of vibrations. It could be on your hub. There's so many places where they'll throw sensors, and there was a graphic that had a bunch of places where they put sensors, but I can give you actually a link to the paper that this came from. Every once in a while I get nerdy and will really enjoy pulling out a paper. But they can put all these sensors there, and then they don't have to send you up the turbine. But they do still have to have you watch it. So it's safer for you for working. So you still get to work, but it's kind of like the nerdy work, where you don't necessarily get your hands as dirty as often. Now, why bother? Is that the only reason? Because it's safer for employees? Or maybe I don't have to send you out remotely. Well, no, vibrations start to change really early in the process of something breaking down. Doesn't take very much to change vibration. An example, just this week, I took my car in to the dealership. We'd had a noise in it. And I noticed in the last week, I was getting the noise constant. I had somebody driving with me and they said it was like a child knocking in the back. It was maybe a little creepy analysis, but it was this constant knocking, like somebody knocking on a door. As I sped up, the knocking got faster. As I slowed down, the knocking got slower. So I knew immediately that that knocking was periodic. It was related to the turn of the axle without even checking to see what it was. If only we had a check to see what it was, it would have been a little easier repair, but all it was loose lug nuts. The wheel was slightly loose. And because the wheel was a little bit loose, we were causing trouble. And there was another chatter noise that used to show up periodically. And there was a brake caliper, or not a brake caliper, a brake pad that wasn't, it wasn't secured properly, we'll put it that way. And that was it, because it was a little bit loose. Whenever you hit your brakes, you'd get this periodic noise, and it was just listening to vibrations is what gets you, you know them with your car, and as they change, you know you need to adjust things, and turbines are the same. You'll get to know the sounds of particular things that you're working on all the time, but if they can install sensors and watch vibrational analysis, it's a really cool way to look at it. So, you know, so that's one of the earliest detections. A little bit further down the line, you'll see changes in oil. Then they get, well, you can hear the change. Eventually, well, that's where I was at. I was at the point where you could hear the change. Eventually, you get to the point where there's heat. Thankfully, I didn't get down to the breakdown point, and my wheels all stayed on the car, and now they're nice and tight. The car is quieter than it's ever been. So I wasn't crazy in figuring out what was going on. But vibrational analysis is really good thing to kind of look at. It's actually really cool, and I think it's probably one of the futures of early detection in repairing a lot of things. I think it's something that we can use for a lot of mechanical components. Now, when I was in school, we used vibrational analysis to analyze molecules. So everything around us vibrates, whether we realize it or whether we don't. And we would take compounds and we put them in usually deionized water. We put them in an NMR, nuclear magnetic resonance. And what it would do is it would look at the electrons inside, and it would tell us what the vibrations were on them. And from where the peaks showed up, I could figure out, well, oh, those peaks, are they from the heavy parts or the light parts? And I could actually figure out the structure of what I made just looking at a picture of what the vibrations of the molecule look like. So it's actually really, really cool that they can use it for really sensitive stuff, and you can use it for really complicated things, much like you would have in a turbine. So that's all I'm doing for this section. Hopefully that hasn't been crazy confusing. The assignment for this section is going to be probably going to be pretty straightforward for you guys. It's one that I can't really do a whole lot of a quiz on. So it'll be hopefully a nice, easy kind of discussion piece for you. And next, we're on to vectors. All right.